Today I'm going to teach you how to make an electric generator, AC generator from an induction motor. This looks like BLDC, but it is mono block pump with a power rating of around 100 watts, 0.5 amps, 220 volts and rest the power factor. As you can see guys, that the shaft is running really smooth, indicating that there are no magnets inside and it's an induction motor. And guys, because it's a pump, these two pieces were also connected to its head, and internally they contained an impeller for performing the pumping action. And you can imagine now how it looked. Okay, so let's remove this. Now guys, at the back of it you can see 4 terminals. Okay, 2 are for starting the motor, to which the capacitor will be connected, and these 2, the red ones, are for the main winding. So guys, here as you can see that I'm connecting the meter terminals to the main running winding of the induction motor, which are the red ones. And the meter, as you can see, is pointed at AC voltage measurement mode. The starter windings are not connected anywhere, they are just left open. And now I'm going to run the shaft and hope that it generates some voltage. You can see that it is generating very little voltage, somewhere around 0.07 volts, which is very less. So I decided to couple the shaft with this cordless drill and then try. Okay, now let's hope that it generates some good amount of voltage. So at full speed it is generating around 0.2 volts AC, which is very less. And that was because an induction motor contains a squirrel cage rotor without magnets. Okay, so let's open it up and do some modifications and then try. Now guys, yesterday I saw a video on how to convert an induction motor into an electric generator, posted by Great Scott. Yes, I follow him and really like his content, but I have a different point of opinion on the fact if induction motors can be converted to generators. Like he said that they are not useful as a generator and they generate around 2 volts or something like that, which is not useful at all. And if you want to use it as a generator, then you will have to either modify the windings or use stronger magnets. Now guys, this what you see is my custom made rotor field from an old DC armature, and the magnets are from a 775 small DC motor, and that also not the strong ones, only the ferrite magnets, not the neodymium magnets, which I'm using here to induce EMF in the armature windings of the induction motor and see how much voltage it generates. So let's try that. Here as you can see that I've placed a bearing, okay, and the black wires I have taped them over here on the yoke because they were getting in the way of testing. So okay, it's like this, and I'm going to measure the voltage or generate electricity from these 2 wires. I mean, it is going to be present on these 2 also, but I'm not going to like measure it with a meter or utilize it. Okay, now one thing you will notice, okay, this is the winding and that's the core and the armature. Now when I'm going to place this magnet, the field winding, the field, not the winding, because it contains magnets, and place it through the hole of the bearing, okay, there is a lot of air gap. I'll show you. You see the air gap, so much air gap is present, so the voltage that is going to be induced is also going to be really less. So then also considering that, you will see the generated voltage is going to be much more. So guys, here as you can see that I am connecting a cordless drill so that I can rotate the field and the induction motor can act as a generator and generate electricity. So guys, here as you can see that there is a little movement of the drill, no rotation at all, and still it is generating some voltage. So let's start it. You see that it is easily generating around 6.7 volts. Let's try and go a little more. 7, 11, so 12.17 volts AC was the max I could do with just 2 poles. So much air gap between the field poles and the armature, and also the lowest quality of magnetic poles, the ferrite poles, and that also very small and too old from a 775 motor. And yes, I have also not utilized the output voltage from the starter winding, these 2. So let's do the measurement for these also. Keep watching the display screen of the multimeter. You see around 13 volts is the voltage produced from the starter winding. So 12 volts from the main winding and 13 from the starter winding. Now guys, this is an 84 LED panel. Okay, I haven't tested it. I don't know how beautiful it is going to glow and how much output illumination it is going to give. But still, let's see if it works or not. Okay, you see the flickering is because the output is AC, obviously. So let's turn off the lab lights and then see how much the output illuminance is. So guys, the lights are out except for the camera flash. Okay, you can see how bright it is. Let's turn off the camera flash as well. Now all the 84 LEDs except for these three, I don't know why they're glowing so little, but yeah, rest of them are working just great. Yeah, I think I found one more over here. I don't know much about it, but there's a little pointed towards the top and below. That is the max variation that I am getting over here. And the frequency that you can see is only 21.36 Hertz. That depends on the RPM that I'm giving it here. I will reduce the speed, then you will see the frequency. You see 9 and 10 Hertz, and if I increase it, 21 Hertz. Okay, and so we can reach 50 or 60 Hertz according to our requirement. So yes, the output sine wave is also pretty good and the output generated voltage is also very good. And guys, if we use a bridge rectifier, we can get a constant output DC also. You see, still there is a little bit flickering present, and that can be eliminated by connecting an output DC capacitor across the two terminals. You see, pretty good, right? Let's turn off my camera lights. Still glowing and slowing down because of the charge left in the capacitor. So guys, I believe that was enough proof for you that an induction motor can be converted into an electric generator, an okay one. I'm not going to say a great one, but yes, it can be converted and utilized as an electric generator. But now comes the part why it didn't work when Great Scott tried it. Now guys, let's assume that this one is one of the induction motor coils in its armature, okay, and this is its rotor, the squirrel cage rotor, and we have managed to place a magnet on this side and one on this side. Okay, so the coil is like this and the magnet is like this, and this one is north, the magnet, this one is north, okay, and this one is south, this side. So like it moves like this, then it induces voltage, and then again when this magnet comes, then it induces reverse voltage, so it produces pure sine wave AC. Okay, that is easy. But what will happen if we place the magnets too close to each other? That happens when we like introduce many magnets, like as Mr. Scott did. What he did was he used like 8 magnets, because of which they were too close to each other. This time when it comes, then you see and you tell me what will happen. Okay, what do you see? You see 2 magnets inside, so the 2 magnets are inducing EMF in the same coil. Let's say this portion of the magnet, the surface is north. Okay, this north side of this magnet is going to induce south on the front side of the magnet. This side is the front side of the magnet. Okay, it is going to induce south over here and north at the back. And at the same time, this is having south on its surface, the other magnet. So this magnet is going to induce north on the front and south at the back. So they both are going to fight each other, and whichever is a little stronger than the other one, that is going to override the other one. And the difference between the strength of magnetism is the only available magnetism that is going to induce voltage in the coil, and hence very small output generated voltage. This, what you see, is a Vanco KBPC 3510 bridge rectifier, single phase with a maximum current rating of up to 35 amperes. So today in this video I'm going to modify it into a 3-phase rectifier for wind turbine generators. So these, what you see, are diodes, okay, and each diode has a rating of around 6 amperes. So I'm going to use these to convert this single phase into a 3-phase rectifier and with a current rating of up to 18 amperes. So guys, the first step is to make 2 sets of 3 diodes, okay, 3 on this side and 3 on this side. Let's keep these on one side. Now this gray side that you see, this indicates the negative. So what I'm going to do is connect all the negative sides of these 3 diodes together, okay. So let's do that. So guys, the soldering part of the first set has been completed. All the negatives on one side and all the positives on one side, okay. Same for this set, all the negatives and all the positives. Now guys, both the diode sets have been completed, okay. This is the negative side for all the 3 diodes and same for this one. So let's talk about this set, okay. So the negative side of this set will be connected to the positive stated terminal of this rectifier, okay. Okay, let's move on to the next one. Now guys, in a rectifier, if this side is positive, then its diagonal opposite is the negative, okay. So this one is the negative terminal of this bridge rectifier. So to the negative terminal, the positive side of the diode will be connected, which is this side, okay. Gray one is always negative, so the other side automatically becomes positive, okay. So let's do that. Yeah, positive terminal of the bridge rectifier has also been connected. Now this one and the diagonal opposite, this one, these two are the AC terminals. So we will connect the wires afterwards, but this one to which the diode has been connected and this one to which the other set of the diodes has been connected, these two are the plus and minus output terminals for the 3-phase DC rectifier. And since the output current is high, so I'm going to connect the wire of similar rating, okay, to this one and this one. So let's do that. So guys, here as you can see that I've connected the 2 wires to the positive and the negative respectively, and now comes the time for the 3-phase AC terminal connection. The first one is going to be this one at which the diodes meet, okay, this point. This will be connected first, and to this terminal I'm going to connect the red wire. So guys, now comes the final connection. Okay, let's turn this wire like this. Like this side is going to be the 3-phase side and this side is going to be the DC high current output side. So 2 more wires are needed, which I'm going to use these. So let's take blue one. Doesn't matter which color wire you take, all of them are AC. So you see this terminal, okay, here as I showed you, it's showing the AC sign. So this will be connected over here like this, done. And this terminal black, this will be connected to the last terminal that is left out, and move it like this. Same for this one. And we have our 400 volts and up to 18 amps 3-phase full bridge rectifier. So guys, the part 1 was about the construction of this 3-phase rectifier, and this part, the second part, is going to be about its testing with the help of this 3-phase brushless generator, which actually is a motor, but I'm going to use it as a generator. So guys, for the connection of the rectifier to the generator is simple. this and this. These three wires are the three-phase wires which will be connected to the three terminals of the three-phase generator. Okay, so let's do that. Done. Second also done. And yeah, so all the three wires from the bridge rectifier have been connected to the alternator, after which comes your multimeter. Now to the final DC output terminals from the rectifier, the multimeter pins will be connected. And first what we are doing is the voltage measurement. So giving it the simple hand rotation, you see 2 volts and no locking at all because there is no load, it's only voltage measurement. Let's see the maximum I can do with hand rotation. 5 volts. I think there were 5.1. So 5.1 was the max I could do. Let's move on to the rope testing. Keep watching the display screen. Okay, go. So as you saw, it was 24 volts DC maximum, no short circuit, perfect. Moving on to the load testing. Let's remove the terminals. Now here what we have is a 55 watts car headlamp bulb that I am connecting to the rectifier output terminals. Okay. So you saw that it was glowing, but obviously it was a little hard for me to rotate the shaft when it was under load. Okay, that was pretty bright. Let's turn off the lights and give it one more chance. I have turned off the lab lights completely and now only the camera lights are on. Okay, that was pretty awesome. Now guys, I have another better replacement for this generator. Okay, this is not actually a generator, it is a BLDC motor that acts like a generator when rotated, which is this one, a real wind turbine alternator, 400 watts. So let's do the connections, and obviously it is going to generate more power at the same input load, because the difference between a wind turbine generator and a BLDC motor is the matching between the number of stator and rotor poles. So guys, I've done a little change. I've placed the alternator on a vise and the three wires have been connected to the three-phase bridge rectifier with output connected to the 12 volts bulb. Okay, so let's get on with the test. Okay, first I'm going to start easy. You see it is glowing pretty good. Now I'm going to put more power to the shaft, and I've also turned off the lights, and yes, increased the length of the rope because the pulley is bigger. Okay, go. Wow. You see that at the same power, I would say that it was a little bit easier than before. Once again, see. So guys, here as you can see that I am using 2 aluminium foils and 1 cling wrap, and there is another blue cylinder like thing which I'm going to tell you afterwards what it is and why I am using it and how you can get it. So guys, this what you see is an old water purifier membrane. You see it's showing membrane element, it's discarded, and I wanted something to roll these 2 foils and cling wrap on. So I'm going to use these. You can also use a hollow PVC pipe for the same purpose. So anyways guys, the first step is to take the cling wrap roll and spread it. After that, take the first aluminium roll and spread it on the cling wrap roll, and then spread the third aluminium roll and place the set of cling and aluminium roll on it, and then place the membrane cylinder on it, and if you are using a PVC pipe then place that on it. Then also create sharp edge cutting of the aluminium and cling wrap set to prevent any contact between the aluminium sheets, because that can create a short circuit and damage the project. So guys, after completing the wrapping part of the aluminum foil around the membrane, I will tell you a very important part, which is that we always have to make sure that the 2 aluminum sheets don't get in contact with each other electrically, because then it is going to create a short circuit and our capacitor is not going to work, and probably the power supply that you are going to use to charge the capacitor, that is also going to get destroyed. Now guys, before fully completing the rolling same process of the aluminum sheets, you will also have to use two wires to give access to electrical connection to both the sheets, aluminum sheets, for using it as an electric capacitor, power capacitor. So guys, after stripping off the wire insulation comes the part of placement of the wires. So first take the red wire and place it on the top aluminum sheet by folding it to create double contact area between the sheet and the wire, and then simply roll it over. And after doing that, take the second wire, which is the green wire I'm using, and take the cling wrap and create a space between the lowest aluminum sheet and the cling wrap and insert the wire in between the empty space, and then roll it again. And after that, roll the sheets until the full 9-meter aluminum sheet is utilized for the project to create maximum area for better capacitance in this capacitor making project. Here, as you can see, that I've used this tape to keep the aluminum foil in place because the wrapping part finished over here, and these are the two wires that I took out from the membrane by creating the diagonal drilling. Okay, so with that being done, it is quite steady and rigid. Obviously, because it is just a foil wrapped around a membrane, you can also use a PVC pipe. Let's put it to test. So the first part of the test is the conductivity test to make sure that there is no short circuit, which is a high probability. Here, as you can see, that I have pointed the meter knob to the resistance check mode, and here it is showing 0 ohms. So if there is going to be a short circuit, it is going to beep. So as you can see that there is a beeping sound which indicates that there is a short circuit which I have to rectify. So guys, after carrying out all the precautions and checking if there was a short circuit, I still tested and it beeped. Yeah, like this. And it continues to beep, which made me do more tests on real capacitors that we get pre-manufactured. Okay, then I tried this. As you can see, this is an AC motor capacitor, 68 microfarad, and if I connect the multimeter, see, it's not beeping over here, but well, it beeped initially. You see, it beeped, and now it stopped beeping. Okay, now when I reverse the terminals, then again it beeped and stopped beeping, which means that it is charging and discharging, something like that is happening in this AC capacitor. Okay, and the capacitance of this capacitor is much higher, because of which it is beeping a little longer. You see, it is beeping and beeping and beeping, which indicates that a capacitor beeps until it gets charged by the battery to the voltage that the battery provides. At least I think it's that, I'm not sure, but this is something really different, that it keeps on beeping. Like this one beeps, I think, because its capacitance is very high, like 41,000 microfarad. Okay, but this one beeps only for like 1 or 2 seconds and then it stops because its capacitance is only 80 microfarad max, as I showed you. You see, it stops. So this made me think that there is no fault within this capacitor. Okay, yeah, I think now it is not beeping because maybe this one is also charged. So guys, I did one more test to make sure that a multimeter produces an output voltage at its pins when we do the resistance check. Okay, so for that I used two multimeters. One is already this one, and the second one is this one. So this multimeter, I have pointed it to 20 volts DC to confirm that if it produces some voltage, then this is going to display it. Okay, so these are the two pins that you see. These are from this multimeter, keeping it like this, and we have the two pins from this multimeter here, keeping it like this. Okay, so now if we touch the two pins, you see that it is actually producing some voltage that is being displayed over here to the multimeter. So this confirms that the capacitor was actually charging to that voltage, because of which it continued to beep. okay, and once it would have gained that charge, then the beeping would have obviously stopped, just as in the case of this AC capacitor. Now guys, there is no insulation around this newly made capacitor, and the charge, when it charges, can get discharged from the air around it. So I have to like minimize that discharge. So for that I'm going to use this black insulation sheet. Okay, so guys, here as you can see that the capacitor bank, homemade capacitor bank, is completely ready now. Okay, and this is going to isolate the internal metal sheets from the air around it or moisture around it. Now this, what you see, is a power supply. Here you can see 32 volts DC and 5.6 amperes, which I'm going to use to charge this capacitor bank. Although this is an AC capacitor because it contains only 2 sheets and a cling wrap, but it is also going to charge on DC. So guys, here I believe that the capacitor bank is charged now. So let's conduct the short circuit test first. Okay, seems like it is charged. So let's touch the 2 wires over here and see if it creates a short circuit and a large spark. Okay, you see the capacitor is working. You can see that I'm touching and removing the terminals because at the beginning the capacitor creates a short circuit, because of which the power supply turns off. So guys, as you can see that the lights have been turned off and it's time to do the short circuit testing. Okay, now guys, this what you see is a 9 volts to 32 volts car headlamp bulb night eye. Okay, it also has a BLDC fan at the back of it. Link to buy will be provided in the description, you can check it out. So I'm going to try and glow this bulb with this capacitor bank and see for how long can it hold the charge. Yeah, I think the charging is complete now. So let's touch the terminals to this night eye, but the voltage is just to its maximum, so there is a high probability, even if it is like 0.1 or 2 volts high, it is going to fuse. But let's see what happens. Okay, you see that it glowed for like 2 or 3 seconds and then it turned off. So guys, let's charge the capacitor once again in the reverse direction. This time I'm using black wire to the red and red wire to the green one. Charged by now. So now it's time to connect the terminals of this motor to this capacitor bank and see if it can run it. Okay, you see it is running and slowing down because the capacitor is now discharging. Well guys, this one what you see is a 36 volts 15 amperes DC motor, really big. Okay, so I'm going to try and run this 15 amperes high current motor with this capacitor and let's see if it can start it for a few seconds or so. To make sure that we can realize that the shaft is moving from far off distance, I'm going to place this big clip on its shaft. Okay, like this. Seems like the capacitor bank must be charged by now. Let's touch the terminals of the DC motor to the capacitor and see some shaft movement. Whoa! Well, it was very dangerous. So guys, I hope you liked this video and learned a lot from it on how to make a capacitor at home from aluminum foil. So thanks for watching. Hit like and subscribe.